Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We shall also learn how to compute percentage voltage regulation of this line using those constants when load details are given. A three-phase 132 kilovolts 50 Hz transmission line delivers a balanced load of 70 megawatts at 0.8 power factor lagging. The line constants are resistance per phase equals to 15 ohm, inductance per phase equals to 120 millihenry, and phase to neutral capacitance equals to 0.84 microfarad. Neglecting ligands and using nominality method, we have to determine the ABCD constants, the sending end voltage, the sending end input power, and the percentage voltage regulation. Let us first write down the given data. Power delivered to the load PL equals to 70 megawatts, that is equal to 70 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 70 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3 into 0.8, that gives us 382.7 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 382.7 ampere at an angle minus 36.8699 degree. In this case, load current IL is the receiving end current IR. Given supply frequency F equals to 50 Hz, resistance per phase R equals to 15 ohm, inductance per phase L equals to 120 millihenry, that is equal to 0.12 Henry, and capacitance per phase C equals to 0.84 microfarad, that is equal to 0.84 into 10 to the power minus 6 farad. Let us now compute inductive reactance per phase XL equals to 2 pi F into L. Using values we get 2 pi into 50 into 0.12, that gives us 37.7 ohm. and capacitive susceptance per phase Vc equals to 2 pi f into C. Using values we get 2 pi into 50 into 0.84 into 10 to the power minus 6. That gives us 2.64 into 10 to the power minus 4 mho. Series impedance per phase of the transmission line Z equals to R plus JXL, that is equal to 15 plus J times 37.7 ohm. This may be written in polar form as 40.5745 ohm at an angle 68.3 degree, and shunt admittance per phase Y equals to J times Vc, that is equal to 0 plus J times 2.64 into 10 to the power minus 4 mho. This may be written in polar form as 2.64 into 10 to the power minus 4 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 40.5745 ohm at an angle 68.3 degree, and shunt admittance per phase Y equals to 2.64 into 10 to the power minus 4 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 2.64 into 10 to the power minus 4 at an angle 90 degree into 40.5745 at an angle 68.3 degree. That gives us 0.01071167 at an angle 158.3 degree. This may be written in Cartesian form as minus 0.009953 plus j times 0.0039606. Now we shall calculate 1 plus 1/4 of y into z, that is equal to 0.997512 plus j times 0.0009902. This may be written in polar form as 0.997525 at an angle 0.05688 degree. For nominal T equivalent circuit, A equals to D equals to 1 plus half of y into z, that is equal to 0.99502 plus j times 0.00198. This may be written in polar form as 0.995022 at an angle 0.114 degree. B equals to z into 1 plus 1/4 of y into z. Using values we get 40.5745 at an angle 68.3 degree into 0.9975125 at an angle 0.05688 degree. That gives us 40.47357 ohm at an angle 68.35688 degree, and C equals to Y, that is equal to 2.64 into 10 to the power minus 4 mho at an angle 90 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have computed receiving end current IR equals to 382.7 ampere at an angle minus 36.8699 degree, and generalized constants for T equivalent circuit A equals to D equals to 0.995022 at an angle 0.114 degree. B equals to 40.47357 ohm at an angle 68.35688 degree, and C equals to 2.64 into 10 to the power minus 4 mho at an angle 90 degree. Expression for sending end voltage per phase Vs equals to A times Vr plus B times IR. Using values we get 0.995022 at an angle 0.114 degree into 76,210 at an angle 0 degree plus 40.47357 at an angle 68.35688 degree into 382.7 at an angle minus 36.8699 degree. That gives us 89,039.06 plus J times 8,240.98 volt. This may be written in polar form as 89,419.617 volt at an angle 5.288 degree. Expression for sending end current per phase Is equals to C times Vr plus D times IR. Using values we get 2.64 into 10 to the power minus 4 at an angle 90 degree into 76,210 at an angle 0 degree plus 0.995022 at an angle 0.114 degree into 382.7 at an angle minus 36.8699 degree. That gives us 305.08992 minus J times 207.75095 ampere. This may be written in polar form as 369.1 ampere at an angle minus 34.2529 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 89,419.617 at an angle 5.288 degree divided by 0.995022 at an angle 0.114 degree. That gives us 89,866.975 volt at an angle 5.174 degree. Let us now calculate voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 89,866.975 minus 76,210 divided by 76,210. That gives us 0.1792 per unit or 17.92%. We have obtained sending end voltage per phase Vs equals to Vs at an angle delta equals to 89,419.617 volt at an angle 5.288 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 369.1 ampere at an angle minus 34.2529 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 89,419.617, which is approximately equal to 154.88 into 10 to the power 3 volt or 154.88 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 5.288 degree plus 34.2529 degree. That gives us 39.5409 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 39.5409 degree. That gives us 0.7712 lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 89,419.617 into 369.1 into 0.7712, which is approximately equal to 76.36 into 10 to the power 6 watts or 76.36 megawatt. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We have also learned how to compute percentage voltage regulation of this line using those constants when load details are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.